Here's a tiny little program that can be built and run. It doesn't do anything special or fancy. Really all it does is push RAX onto the stack and then immediately terminate. It doesn't ever pop it off, but again, that's okay because remember, before underscore start, the stack didn't exist, the process didn't exist, its memory map didn't exist. Linux built all that specifically for this process, and as soon as we tell it we want to exit with that syscall, Linux removes this from the scheduler and deallocates all of our stuff so the stack goes away. So it doesn't matter that the stack was unbalanced. No one's going to care. So we can build this. And we could run it. It's not going to do anything. Hooray. The more interesting thing is to do an obj dump of it. And you can see right here, push RAX turns into a very simple command, very simple single byte instruction, and that's pretty neat. All right, so that's pushing 8 bytes onto the stack, right? Because RAX is a 64-bit register. What if we wanted to push something else on the stack? Well, for the most part, you need to be pushing 8 bytes at a time on the stack. That's what you need to be doing. Multiples of 8. What if I wanted to push AX on the stack? Now, AX is just 2 bytes. It's a 16-bit register. Will the system let me do that? Well, it certainly assembled. And nothing bad happened when I ran it. And here's what's in it. Well, pushing AX actually requires an extra prefix byte to say, 50 would be push RAX. This says no, just push the low 16 bits. Pushing a 2-byte value on the stack is really a bad idea because the stack ends up in this weird state where it's off by 2. You always want the stack to be at a multiple of 8 if you can do it. But the system allows you to push a 16-byte or 16-bit register. I don't know why it does. Let's try one more thing. We pushed RAX, we pushed AX, let's push EAX. What happened here? You can't push a 32-bit register onto the stack. You also can't push a single byte. You can only push full 64 bits or 16 bits. I don't know why that's the way it is. It seems crazy, but that's the way it is. And again, 8 bytes. You're pushing RAX, or you're pushing RBP or RSP. You're always going to be pushing 8 bytes on the stack. You could push just 2. Please don't do that. You want the stack to be aligned. In fact, there are times when you want the stack to be aligned on a 16-byte boundary. And we'll talk about that. If you're going to be using the XMM registers, you really need the stack to be aligned on a 16-byte boundary. Enough of that. What's on the stack when my program starts up? Well, for that, I wrote a little assembly language program. And it might be worth taking a look at because I threw the kitchen sink into this little assembly program. And it's got macros and it's got all kinds of good stuff in it, I think. And so it's called ViewStack. We can go ahead and build it. And it builds a position independent executable. And we can verify that. And you see, there it is, dynamically linked, etc. So when we run this, I'm going to pipe it to most, we get lots of information about the stack. So we're told where the stack pointer is, and because of address space layout randomization, this value is going to change. We're told what argc is. We can look at the top 10 things that are on the stack. So over here in this column, we have how you might reference it in your assembly, right? This is RSP plus 0, RSP plus 8, RSP plus hex 10, hex 18, and so on. Here is the actual address, and then here is the quad word content, right? The 8 bytes that are there. Then we look at the command line arguments. In this case, we see that there's view stack. That's the name of the thing that we're running. If you haven't watched the video about the exploit, you might be curious about what happens if there's not anything there, and it turns out sometimes that can lead to an exploit. And there's the terminating null for those. In addition, after the arguments is the environment. And so here is the environment. We see that starts at RSP plus 18 in this case. And lots of stuff in the environment. Scroll past all that. After, there's the null terminator for it. After the environment, we have the auxiliary vectors. At some point, if there's time, we'll talk about what the auxiliary vectors are. But they come next on the stack. And there they are. And this prints them out. And we know they terminate when you have null, null. So the first thing is the type of the vector. The next thing is the contents of the vector. All right, so there we go. So suppose I ran view stack and I gave it some argument. Let's say I gave it the argument foo, and then I gave it 1 and 1.5, and I gave it 0x21, and I gave it Tony Hawk. All right, let's go ahead and do that. And so now we see that argc is 6, and we see that the thing at the very top of the stack happens to be 6. This is also argc. And then here is what's in argv, starting at RSP plus 8, right? So at 0 we have this, at 8 we have a pointer to the string view stack, then foo 1, 1.5, 0x21, and Tony Hawk, and then a null. So you can see how the information is being passed to us. It's being passed on the stack. And argc is the first thing at the top of the stack when our program is started. Now, if we do anything, we push something on the stack, all of these offsets change. So suppose we come in to start, and the first thing we do for some reason is we decide to push RBP. We don't need to, but let's say we did. If we did that, then these would all increase by 8. So it'd be RSP plus 8, and that's where we'd find argc. And RSP plus 16 would be where we'd find view stack, and so on. So there you go. If you'd like to see how this program works, it's kind of interesting. It is in 2 pieces. There's the main piece, but it actually includes another file. And I've put some comments in here to sort of help you understand what's going on. And it's a moderately long program with a lot of information in it and some fancy use of macros. That's it.